quantum computing people offer them jobs right away to get them there, and I lose them fast. This story started actually by my supervisor, Melsinos. I did my PhD in Rochester, and then at Brookhaven National Lab, we had our launched the first experiment. The big thing about that, all of these people, most of these people are to operate the cryogenics. It's an amazing thing. You had to have a whole team of cryogenics experts to run the experiment. What I did in this experiment as a graduate student, nobody asked me to do this, which was interesting. I said one day, because every time we would tune the axion, take data, and then move it manually, right? And I said, I said it actually, I didn't dare to say to my supervisor, I said to another graduate student, I said, I can do this automatically. It was, they didn't believe it. They said, yeah, sure, yeah, try it. And that way we could take data around the clock, okay? I also discovered the first fake axion because one background signal went through the system, and it was a really good. It's too bad it wasn't the real one. And well, maybe we will discover one day a real one. My supervisor passed away last year. He was really a daring pioneer, full of energy, great teacher. So we put the first limits. This is Rochester, Brookhaven, Fermilab, and University of Florida. It's that line over there, because what they did is University of Florida, they integrated for a long time, but you cannot integrate out this. It goes with the fourth power. It just, you lose patience after a while. All right. And the ADMX actually accomplished a great deal. This was KSVZ level of 2010 and DFSZ 2021 and so on. If you look at the frequencies, you'll find that most everything is below 1 gigahertz. That's because the magnet, niobium tie magnet, regular cheap magnets, can be large, and the microwave cavity can be large. So and John Clark, he told them, I can get you a squid amplifier to give you good noise level. So they did all of that, and they accomplished what they did. So it was a good choice to go there. But above a gigahertz, you fall off the cliff right away. Okay? This is from ADMX, David Tanner. And I won't go into the details, but once you want to go to higher frequencies, you make the resonator smaller and to resonate at higher frequencies. And now you see how many orders of magnitude you go down. All right? So this is when the IBS came out, 2011, and what my idea was the following: if the problem is big enough, we can put enough resources to solve it. That was it. I didn't know how to solve it. I had some ideas, the directions. And this is what we did. It was the idea was to use, this was from my proposal to IBS, and HTS magnets, they could go up to 40 Tesla. That was the idea. And I knew these people, they could make the magnets. So we started working on that. All right, this is 120 photons, all right, without external coupling, and about 30 photons per second with optimum coupling. So we put we made a few magnets, 8, 9, 12, 18, and we almost did the 25, but we ran out of money. But anyway, we have this, and we developed the cavity quality factor, amazing things. They were telling us this is impossible, and the engineers from the review committee said, no, this is impossible. They were cutting our budget twice in 2 years because it was impossible. And when we did it, instead of being happy, they were insulted. I mean, this was a great accomplishment, right? Anyway, we did this. Now the whole world is looking at us, how to make those. Then we did a lot of other things too. So let's go here. The magnetic field, dFdt goes as p to the 4th power. So you can gain big time here. We did the so-called pizza cavities and then dielectric cavities. We gain a factor of 3 in dFdt or 5 with the dielectric cavities. HTS, it's amazing. 1 to 2 orders of magnitude already achieved. Near quantum noise here. And we developed a new method. This is completely conceptually new method. It was done, by the way, all by Koreans. Okay? Never be scared. This is Koreans doing that. Absolutely.
Why your KDT called pizza cake?
You'll see. You'll see it. It looks like a pizza. Yes. So what we did under a bright lamppost with microwave resonators based on niobium-3 tin magnet for that, 37 liters, powerful dilution refrigerators. I mean, Koreans are excellent engineers, all right? When we build a system, they work, they function, they know how to operate them and so on. That is never a question. The question is, could they come up with new methods, new innovative methods? And this is what we changed completely. They are not afraid to try new things and to fail, all right? Because failing, it doesn't feel good. But they overcame that, all right? 25 millikelvin, nobody has anything like that, all right? JPAs are the best in the world, and so on. Microwave cavities, high frequency efficient, high quality factor. This is how we started, okay, at KIAS. Actually, we got 2 of those empty places, all right? And we had to buy even screwdrivers. I mean, completely from zero, nothing. There was, in Korea, there was no experimental axion physics whatsoever, 0. And this is what we had to create a miracle. We had to walk on water, run on water, all right? Several parallel R&D efforts, high-risk projects, high potential payout, established decision-making process. And this was an interesting thing. Young people could be correct. This is an interesting thing because I realized the young people would never contradict the seniors. And it's very dangerous. I mean, it's very expensive in time and so on. All right, and because the seniors would be insulted if they are not always correct. But we changed completely this. Now we are all comfortable for being wrong because we've all been wrong so many times. All right, so this changed completely the atmosphere. And high safety standards, by the way, because the system has a lot of potential energy, and it's important not to lose anyone. And we've applied a lot of experience from the US. Right, all of that. I mean, it really was an amazing, exhausting process, but it worked. So we did all of those things. And if you visit the center, what you find is a can-do environment. I mean, these people know they can do things. They can do things that people thought it was impossible. in its fast pace. As I always say, the Korean clock runs 3 times faster than any other clock, all right? And you better believe this, absolutely. Now, if you go there, it's full of experiments, absolutely several projects. So we use this again to show you what we have and so on. I mean, these are an amazing targets. Now, let me tell you a little bit about HTS. Why HTS? And it's critical how this thing worked. You have to prepare yourself to get lucky. You have to create the opportunity for luck to come to you, okay? HTS, high temperature superconductors. All right. The LTS, this is the conventional ones. They are superconducting, but you may know, excuse me, LHC, the LHC magnets work up to 9 Tesla. Okay, they even pump the liquid helium so it runs at lower temperature than 4K because they want to squeeze even a little bit more and more and more, right, to get to higher energy. But above 10 Tesla, this thing falls off the cliff. It's done. It's not superconducting anymore. Well, look at the niobium-13. Niobium-13, where is there it is. You have this and you have that. It's much higher. Niobium-13 is much higher. And HTS can go up to 200 Tesla. Of course, it's expensive. It has a lot of issues and so on. But right now, a magnet that's made of niobium-13, which is our 12 Tesla magnet, it works very well. You can quench it. There's no problem. We tried the HTS magnet itself. We developed this at Brookhaven National Lab. It was going great. With no insulation to make it safe and so on. We built 16 out of 28 pancakes. We had it there. But unfortunately, there was something happened in the society. Nobody liked IPS. And so they cut the budget and we had to cancel it. That's too bad. If we had this magnet, we would have been at DFSZ sensitivity already for the high frequency part. We are on the low frequency already. But let's move on now to the pizza cavity, right? If you put different cavities inside the big bore, magnet bore, this is what you're going to get. This is the scan rate. And if you make it like that, you're going to get this, all right? Now, the thing, there are tricks over there. You have to study this to do it correctly, all right? It's about the tolerance, how big this opening should be. Because if you don't do it right, what you're going to get is mode localization. All right, if you close this opening too small, the energy will be on one cube only. If you make it too big, you're going to lose the energy because it's going to escape, and you have to do it just right. So you keep it there, because when you build things, it's never ideal. So that's the pizza. We made those, and this is how it looks with the energy, right? I mean, it's beautiful. This is from Charles' thesis. He's working now for a quantum computing company in Switzerland. He just finished. And immediately he got the job offer. and this is it. He did this, 100 megahertz. That's what he did, this work, 100 megahertz at KSVZ. Nobody has anything close to this. He used the JPAs. By the way, whenever you use a new system, it doesn't work. It doesn't work. A new system doesn't work. And if you're scared to touch it, it will not work. So you have to go in there and debug it and so on, because there are 10 things you have to fix. He worked day and night to get this done. And he did it. He debugged the whole system. We got the chips from University of Tokyo. We made them work, but he really debugged the system, because the noise, to get down to quantum noise, everything is a problem. If you see any hot surface from somewhere, it will come and your noise will be too high. Your ground has to be perfect, and so on and so forth. So the equivalent of that is, it has no resistance, by the way. That's why you can get down to quantum noise. You have a capacitor and an inductor there. If you start oscillating the capacitor, you can get amplification. It depends on the phase. That's the principle of it. You have to shield it because it sees magnetic fields very well, and shielded so well that that's the difference. This is 8 Tesla, this is 8 Tesla, this is 0 Tesla. You see the difference? Very, very little. 0.04 of quantum flux. Okay? Very little. And people are trying to copy this design to get to that design, because it's a big problem. You have to take the amplifier far away. That means you don't amplify fast enough. All right? And then this is what he got. This is the quantum noise level, and he got it just a little bit over it. All right? He got this. This is the so-called pizza cavity, and this is the limit. I mean, within 10, 20, 30% of KIAS. Now, this team that developed the pizza cavities also developed the next generation of high frequency with the dielectric pulse. This is the metallic one, this is the metal pulse, and this is their idea with the dielectric pulse. And the idea was how to tune this, all this material, how to tune it. They used the kirigami. The father of one of the postdocs, he suggested, why don't you use a kirigami to move this equidistantly at the same time? So get your family involved if you have to. It worked. This is the way we are doing now this experiment. It's actually working right now. Beautiful. Because experimental physics means you simplify and you make it work. Simple things work. Otherwise, you'll be developing or debugging the system. Right. So we have a lot more publications, but I put only the PRLs here. And then the quality factor, 5 million. I mean, people were telling us this will never work and so on. It says just ignored them, did the work, and we moved on. And our target is really to get down to even the sensitivity DFSE, even for 10% of actions being the dark matter. All right? All right, okay. This is from Saturday. I say Saturday over here because they worked around the clock. They didn't have to go home, the weekend and then come back. And it's just they work around the clock. That's because this is important. Wet system, we achieve 5.6 millikelvin on the baseline. And with the cavity, we actually achieved, I saw that with my eyes, 22 millikelvin with the cavity, 37-liter ultralight cavity. We had COVID on top of it. I mean, we delivered the magnet, they delivered the magnet in March, but it was sitting there. We couldn't get an engineer to come. They had to turn it on first time. So we had to do all of this work we had to get a special permission to get the British to come to visit CAPP, Korea. And we involved the Ministry of State, the State Department, and the Health Department, and so on. And finally, we got this through, and we had this person had to be in isolation for 2 weeks before it was allowed to come to the lab. All right, this is with the Korean flag. This is our flagship experiment. This is where we are, 100 photos generated, but look at the noise. If you have 300 millikelvin, which is very good, by the way, the competition has much higher than this, all right? But if you have 300 millikelvin, and this is normal, all right, you get something like 0.5 gigahertz per year scanning speed, all right? So it gets better with 250 and so on. But if you have 150, this becomes 1.7 gigahertz per year, which is good. All right, this is where we are right now. To do this, we had to get to the best in the world. We visited Professor Nakamura at the University of Tokyo. He is one of the original proponents of qubits. Okay, so really top level. We told him, look, we need the chips, but we don't have money. He said, that's okay. It's good science. Real scientists, that's how they work. Yeah, so they are our collaborators. And we got them. And we got good cryogenics experts, because any good engineer can get to 1K. Below 1K is really difficult. Okay, it's another, as they say, it's another solar system. But going below 100 millikelvin, it's truly another universe. It's truly difficult. And that's what we have achieved. We achieved 22 millikelvin, as I said. Typical is 25 millikelvin of the cavity. All right. And we also have a lot of parallel efforts, because you cannot learn this sequentially. You have to do it in parallel, and then all of this effort gets integrated into the big experiment. So we have all of those. And this is what we published in PRL. It was published just this year. That's PRL. And we also got another 60 millikelvin, 60 megahertz. And then we scanned another 150 megahertz. So this is the situation right now. And the PRL sensitivity is at that level. For 20 megahertz, we did a couple of changes to get faster, and things got worse. So we went again, we developed it, and now we are going for the next 300 megahertz, and we believe it will be a better sensitivity. All right? But let me tell you a little bit about the possibility of having high quality factor cavities. If you have a quality factor of 2 million instead of 100,000, which is typically of what we get right now, it's really good, because you can get 2 gigahertz per year even for 20% of dark matter actions, which is an amazing thing. When we started this business, it looked impossible to touch it, and now we are running so fast. All right? For that, you use, again, HTS. All right, and why HTS works so well? The magnetic field penetrates type 2 superconductors, but it moves with the RF, and that's very lossy. HTS has very strong pinning centers, so it doesn't move when the RF is there. It doesn't move. It can go up to 100 gigahertz. That's the thing about that. Strong pinning. This is it. And this is the choice, the tape choice. It depends. People would tell you, oh, I can get high quality factor with HTS, but they are giving you a pencil cavity with very little volume. That's not it. You have to go perpendicular to the surface, and it becomes worse. But you have to use the correct HTS tape for that. This is the student who is now a postdoc at CAPP. He actually processes all of those. And apparently nobody else in the world knows how to do but him and a couple of other students. All right. The very first one, when we had the big success, this is HCS, it becomes superconducting around 90 K. And then we turned on the magnetic field and it dropped like a rock. And we said, all right, it doesn't work. And then it turned around, and we figured out why it turned around. One of the components of the tape was with spins, special spins, and we had to take it out and so on. So we are much better right now. Okay, now this is 13 million, all right, 4.5 million, 13 million, and so on. So now, right now, we actually tested this. We run an experiment. We also run an experiment over here, and it's really going very strong. Right? And we are making a 36-liter HTS cavity for the big experiment. This is from the old HTS cavity, the superconducting cavity in strong magnetic fields. And cap in red. You see over here, this is ADMX. And in red is cap. What is, I believe this is published. PRL, this is PRL, yeah, in red. And then this is what we have achieved already without published yet. And this is what we are going to do the next 3 months. And by the end of 2023, we expect to get to this level. And by 2024, we hope to get that. This is going to be very hard to reach that. We are running out of steam. So we reached that. Some of the accomplishments, 13 million dielectric photonic crystals down to 22, quantum noise limited JPAs, big magnet for that frequency, even 18 Tesla magnet, HTS, new RF. This is a completely new concept. We want to do that to get faster scanning. All right. These are actually, I didn't tell you about the other side of the center, but we are also having a lot of great things over there. G-2, I mean, we accomplished a huge thing, killed 2 systematic errors, CBO, coherent beta translations, and muon losses, the new concepts. All right, these are storage ring proton EDM experiment at Brookhaven. All right. All right, so the Institute for Basic Science was established in 2011. Major investment in basic sciences. We are scanning at DFSZ sensitivity. Nobody was dreaming we would be doing this so fast. Okay, we are on the top of our field. And we have demonstrated the original IBS idea was correct. Unfortunately, IBS decided to phase out CAPP, even though we had a great 8-year review. Which means they got it wrong. Something is wrong. They probably don't understand how bad the decision is, but you know, it's not for me to criticize. These are in blue what's going to happen. That we think we have a chance to go up to 4 gigahertz, maybe 3, but the rest is up in the air. So what works about people, right? It's all about people at the end. It's not the equipment. Engineering, if you have discipline and you crack the whip, you can get good engineering, but not innovation. So what works with innovation, all right? What I witnessed is combine young people's innovation with older people's experience. So you combine that and have a great research subject that helps tremendously, challenging, and small steps, and celebrate success, because most of the time people feel bad. They fail all the time. And when they have a breakthrough, make sure they know that you understand it's a big thing. Adequate funding, because most of the time we fail. Ownership, give them the ownership because it's their work. Confidence building measures while protecting them from failures. I told them many times, your failures are mine, your successes are yours. Checks and balances, exclude gossip. That's a big one in Korea. I mean, I can't shake it off. Okay? Don't work with gossip, forget about it. And prepare for reviews, simple message, and so on. Because irrelevant or people who are not at the correct level, they can do tremendous damage. Now, regular communication with the leadership would be good. That I failed. I can tell you that I couldn't have regular communication with the higher ups. I failed, for sure. All right. And the other thing is the political parties need to declare a ceasefire on basic science because it's too expensive. All right. What one party builds, the other takes down, and so on. And they should get real, because Korea needs a unified front on basic science. Summary, we are on the top of our field. We are going to do the blue. Okay, these are the big things we do. And I believe in the next 10, 20 years, we'll know whether the actions are part of the solution of the dark matter. Thank you very much.